Okay, in this video we're going to be discussing Unit 3C, dealing with uncertainty, and just a kind of a little intro here of where we get uncertainty in numbers, and this happens all the times. Just here's an example. So early 2001, the U.S. federal budget showed a surplus, meaning that the government was going to take in more money than it spent. It had shown that for 4 straight years, and the economists projected that continuing surpluses would add up to about $5.6 trillion over the next 10-year period. And this created some arguments in politics and things, but that's irrelevant as far as what we're trying to get at here. However, in reality, the surplus not only vanished, but over the next 10 years, the federal government went $9 trillion further into debt. So in other words, the difference between the projection and the reality turned out to be about $15 trillion or $50,000 for every man, woman, and child in the United States of America. So how could this projection be so wrong? And in this case, the answer is, like many estimates, those projections are only as good as the assumptions that went into that. And those assumptions were highly uncertain predictions about the future economy, future tax rates, spending, and in fairness, the economists who made the projections were aware of these uncertainties, but again, you can't predict everything, especially in human behavior. And so this story we talk about here of vanishing of trillions of dollars is an important lesson for us, because many of the numbers we encounter in our everyday life are far less certain than we are told, or than we may assume them to be, and we can be severely misled unless we examine. So here are kind of some key terms that we're going to be thinking of: examine and interpret those uncertainties ourselves. And so in this unit we're going to discuss ways of dealing with the inevitable uncertainty of numbers we encounter in everyday life. Now, one big thing about when we're looking at the uncertainty of numbers is what we call significant digits. Again, this is a lot of English here at the beginning, but hopefully it will help create a good foundation for us. So significant digits, this is something that in the sciences, physics, and those type of things you will see very often. And so in this example, suppose you want to measure your weight, or suppose you measure your weight and it's 132 pounds on a scale. That can only be read to the nearest pound. So the scale shows to the nearest pound. So it may show 132, but you might be 131.5 or something like that, and it's rounding. Now, if you were to say that your weight was 132.00 pounds, would be a little bit misleading, because it would incorrectly imply that you know your weight to the nearest hundredth. So when you add that .00, then there's an implication there that you know that your weight is down to the nearest hundredth of a pound, rather than the nearest pound. So in other words, 132 pounds and 132.00 pounds do not necessarily mean the same thing, because the digits in the number, they each have meaning. And so when we look at digits in a number that represent actual measurements, these are called significant digits. So in our example, 132 pounds has what we call 3 significant digits: 1, 3, and 2. And it implies a measurement with accuracy to the nearest pound. However, 132.00 has 5 significant digits and implies a measurement to the nearest hundredth of a pound. So hopefully you can see the distinction there. Even though, mathematically speaking, they are the same number, 132 and 132.00. One has 3 significant digits and is accurate to the nearest pound. The other has 5 significant digits and is accurate to the nearest hundredth pound. And so this idea of significant digits, we're going to talk about precision, we're going to talk about accuracy, and so as we look at these last couple of paragraphs, I'm just going to throw out a couple of things. So for example, in 132.00 pounds, we can assume that these zeros are significant because there would be no reason to include the zeros unless they actually had reference to the actual measurement. However, in contrast to that, we assume that if something says 600 centimeters, the zeros in there, so the last two zeros are not significant because their only purpose is to tell us where the decimal point comes. And so, if we were to rewrite 600 centimeters as 6 meters, we can now see that there's only the 6, which is a significant digit here. So the kind of the location of the decimal and zeros will determine whether or not these zeros are significant or not. So again, it's when we're writing 132.00, if we write it that way, we're intentionally writing those two zeros, which implies that those zeros have significance. However, in the number 600, we've got to write the two zeros, or else we have an entirely different meaning if we just write 6 centimeters versus 600 centimeters. So there are definitely subtleties in counting significant digits, and this can be a little bit tricky for us as we're trying to determine whether a zero is significant or not. Here's another example. If a professor says there are 200 students in your class, for example, without any further information, you have no way to know whether the 200 is exactly 200 or roughly 200. So it's hard to say when we say someone just throws out the number 200. Now we can avoid this kind of ambiguity by writing numbers in scientific notation. So for example, if someone writes 2 times 10 to the second, which is 200, it implies a measurement where we are significant just to, we have one significant digit, we're significant to the hundredth place. However, if someone were to write 2.00 times 10 to the second, that implies exactly 200 students, because the 2.00 gives us 3 significant digits, meaning we want to be accurate all the way down to the ones position. And so this idea of significant digits will help us in dealing with uncertainty and accuracy and precision. And so here's kind of a summary of what I'm trying to get at, and then we'll go over some examples. So I apologize and know that this is a lot of English, and it's a lot to take in, and it can take some practice. But here's kind of a summary of when are digits significant. When do we count them as significant and when do we not? So first off, any non-zero digit, so a digit that is not zero, like 3, 5, 7, 1, 9, anything between 1 and 9, any of those digits, those are always significant. Always. Okay, the next one is a 0 that follows a non-zero digit and lie to the right of the decimal point. Okay, so for example, like 4.20, that 0 is significant. 3.00, that is significant. Those times where it's to the right of the decimal place and we write a 0 that's after our non-zero digits, those are always significant, because you'd only write them if they have significance. Like 4.20, you would either write 4.2, but if you write 4.20, there is a reason behind writing that, if someone were to demonstrate or put out that information. Okay, and then zeros between non-zero digits such as 4002 or 3.06, always significant, because they're a part of those numbers. Okay, now zeros that are to the left of the first non-zero digit are never significant. For example, 0.006. Those 2 zeros are not significant, or the 3 zeros in that matter. Or these 3 zeros right here are not significant. So this would only have one significant digit of 6. This would only have two significant digits of 5 and 2. Okay. And then lastly, zeros that are to the right of the last non-zero digit but before the decimal, such as 40,000 or 210, those are not significant unless it's stated otherwise. That we are being accurate down to the ones, or sometimes you will see this in sciences. You'll see 210, and then you'll see a little decimal. They actually write the decimal with nothing behind it. Every once in a while you'll see that, and that just means we are significant all the way up to that 0. So that's 3. So this would be 3 significant digits, whereas 210 without the decimal would be 2 significant digits. So that's a lot to take in. So I'm going to pause the video right now and just kind of let you synthesize that, and we'll continue on in a part 2.